Okay, hi everyone. Today I'm going to talk about collaborative multi-robot coordination using factor graph. What's the outcome of this lecture? We're supposed to show you how, using probabilistic models, we can first model the behavior of robots and how this model can get optimized when you have some factors between robots that we call them interdependent factors. It has lots of applications, like for example, in when you have multiple robot agents that's supposed to help each other to do a task, like in this scenario, they are helping each other to extinguish the fire in wildfire forest. And we have different robots, different roles. They can play different roles, and they need to collaborate to each other autonomously, find the best place to go. Everything is dynamic here. Fire is changing, wind is effect. So we have some factors for them to make decision. Why collaborative systems are important? Because collaborative systems are more robust. They don't fail if one of the robot break. They are scalable. System performance improved by adding more robots, and sustainable. Robot can share resources and information, and they enable long-term autonomous operations. That's why they are important. I'm thinking the future belongs to multiple autonomous systems to help each other to do the big tasks. How we can model them? In my work, there's so many ways we can model behavior of robot, but one of the good method that I use in most of my papers is using a stochastic model or random process. So we know random process, we have random variables, we have random vectors, and when we bring time between, it becomes random process. So we can model the random process with a graphical model used called factor graph. This factor graph has some states. State is the, for example, position of the robot, and some factors, all the events that happening for decision making to find which state is the best. Those factors are different factors, and we just can bring all of them together in a Bayesian way, and we can maximize this probability. So to do inference and find theta is the states, for example, and E is the events. This, so many people work in that. So, but in a collaborative way, we have actually two different type of factors. For example, some factors are ordinary factors, like a start point, end point. And we have some smoothness, for example, factors. We call them ordinary factors. We have some factors are interdependent factor. When you have multiple robots, they need to collaborate with each other, and they make another type of factors that coming like a proximity safety. Depends on position of each robot, or consistency, how they can act, consistency, or formation problem, for example. And we can bring all of them together in a one optimization problem in a Bayesian method. If we get log and minus log, we can change it to the mean, and because minimization is easier and well-known to solve, and we can use Gaussian-Newton method or Levenberg to solve this in an iterative way. And this is this factor graph. As you can see, there is three robots collaborating to each other. We have interdependent factors, this diamond. As you can see, they are collaborating each other. This is for formation problem. Formation problem is a scenario that I want to talk. We have leader formation. So leaders are trying to stay in a formation, and followers can follow them too. At the same time, we have other things, we have obstacles, we have other factors that can affect their motion. So we need to have some coefficient to see which one is more important. Like, for example, yeah. Anyway, in this case, we have a constant distance, for example, and they are just using constant velocity motion model, and they are following a triangle to from source to go to destination, avoiding obstacle, and reach their destination. A traditional approach using like a centralized method to give them give the leaders order to follow a actually certain like a topology, certain topology. But the method that we are offering is decentralized method. In decentralized method, these robots transferring information to each other, and they share their position and their trajectory, and they optimize them in a consensus way. It's also called Bayesian consensus. So robots exchange trajectories and infer formation consistently. So how we can mathematically define that? For normal factors, we can use just normal factors. For each factor, we have a likelihood of that factor. This likelihood is coming from the cost of that factor. For example, we have cost of factor corresponding to agents AI and AJ, the position of these two, and if they are supposed to follow a certain distance, we can find this cost. So it's very easy. You just need to actually find the distance and check it with D, see if this D is close to that. So we can find the likelihood for each factor. And this likelihood is an exponential family. As you can see, we have some residual. R is residual, and delta sigma is uncertainty. So this is the uncertain method. So we use that in this Python code. As you can see, this green robot supposed to move to the purple. As you can see, they are far from each other and they are not in a certain formation. They're supposed to stay in a 1 meter distance from each other. As you can see, green coming close to them. And when they make formation, they move all together in a certain formation to go to destination. And as you can see in this diagram, we can see that distance start with like a different size distance between R2, R3, R1, R2. And as you can see, they are all make consensus in 1 meter. This is coming from one of my papers, new papers that I supposed to publish next month in collaboration with the Dalhousie University in Canada.